Okay, hi, welcome to this tutorial. We will be talking about which of these are PRFs. Let's first review the definition of PRFs and then go through these PRFs and try to figure out whether or not they are actually PRFs. Okay, so what is a PRF? We can see this in definition 3.9. The main points here are that we have a distinguisher, or like for every distinguisher that exists, we have the distinguisher running with the pseudonym function, so it gets oracle access to this pseudonym function and can query like fk of x for arbitrary x. Or he is in the scenario where he gets access to a properly random function small f, and then again he would be able to query small f of x for arbitrary x. And this whole statement basically says that no distinguisher can know whether or not he's in this world or the other world, meaning that the probability that he outputs the bit 1 in this world with the pseudonym function versus the probability that he outputs the bit 1 in this world with the properly random function, those two probabilities are very close. Their distance is negligible. Okay, and indeed we call this distance the distinguishing advantage. So let's take a look at the first function, which is this f1 here, which just is this candidate pseudonym function, which maps any x to itself. Okay. So take a second to think about it. Is this a pseudonym function? No, this is not a pseudonym function. One red flag is that this key of the pseudonym function is never used. So the output is independent of the key, which is, well, never a good thing for pseudonym functions. And the other thing is that, well, it's pretty unlikely that a random function would map x or every single x to itself, meaning that, yeah, this will be easy to distinguish from a properly random function. And let's actually do this. So let's show that this is not a pseudonym function. How do we show that something is not a pseudonym function? Well, we would have to give a distinguisher that's able to distinguish this candidate pseudonym function from a properly random function. So what does this distinguisher look like? Think about it a bit while I write down the distinguisher. So the distinguisher is very easy. We have this distinguishing machine here, which gets oracle access to some function, we don't know. And then the distinguisher will then query this function on 0 to the n, for like any value, it doesn't actually matter. He will get some y as a result. And then he outputs 1 if this y is also equal to 0 to the n, or like the or 0 bit string. Otherwise it will output 0. Okay, and intuitively this makes sense, right? Because the idea would be that in this in the capital F function, if this is what he's querying in the first step, then he will get 0 to the 1 with probability 1. And if it's a properly random function, then the probability that like properly random function of 0 is also just 0. This would be negligible. So if we formalize this, this would mean that the probability that D given access to the to our capital F 1, to the outputs 1 then, this probability is 1. This will always happen because in the first step he will always get 0. And how likely is it that in this world where he gets the actual random function as oracle access, what's the probability that he outputs 1 then? Well, it's not 0, but it's unlikely, right? So we have seen this lemma here, which is completely overkill for our application, but we can still look at it and like learn something about properly random functions, because this lemma says that in this case, even if I query the function on multiple xi's, and then I query the function on a new x that I haven't queried before, then the probability that I get some particular y is just 1 over 2 to the n. Okay? Even if I've seen all of the other yi's, this is independent of seeing the other yi's. It's always just, I get a uniformly random image if I query a new x. This is how properly random functions work. So when my distinguisher in the first step queries 0, then if he queries this on a properly random function, then the probability that the function also outputs 0 in this case is it's just 2 to the minus n, according to this lemma. We have the special case where n is 0, where the t here, or the number of queries that we do before our last query, that this just, we don't query anything beforehand. Okay, and then we're essentially done, because if we take the difference of these two probabilities here, then this difference is clearly not negligible. It's almost 1. Okay, so this is very small, this is very large, as far as probability goes. Good. That's the first function. Let's take a look at the second function. So the second function takes an actual pseudorandom function, but before it applies this function, it will XOR the input x with just once, meaning that it will flip every single bit of its input and then apply a properly pseudorandom function to it. So, is the result a pseudorandom function? Think about it. Yes, it should be. So let's take a look at why this is. The intuition is that we have a proper pseudorandom function here, this fk, and the only thing that we're doing is we're permuting the inputs. How do we prove something like this? Well, we have to prove it by reduction, right? We have to prove that this here is a pseudorandom function, assuming that this is a pseudorandom function. And we can always do this by doing a reduction. We start with the standard boilerplate stuff. So let D be a distinguisher against fk2. Then from this, we construct a distinguisher against fk. What does D prime do? So this new distinguisher that we're constructing. Well, ideally, it wants to run this this distinguisher D that we have, right? So that if D actually were very successful in distinguishing like our new pseudorandom function from random, then we would hope that D prime, our newly constructed distinguisher, would also be very successful in distinguishing fk, so the thing that we know as a PRF from random. So the image for this looks like this. So this is the scenario that our distinguisher D prime is in. Basically, it will run some code and it can query a function. It doesn't know which of two possible functions it will query if it does. Meaning that either his queries will go to fk, or his queries will go to a properly random function f. So this is the scenario that our D prime is in, and the goal for D prime will be to distinguish which of the two worlds it is in. And in order to distinguish this, it will enlist the help of distinguisher D. Because this is what we do in the reduction, right? We want to use the potential capabilities of D in order to construct our D prime. Good. So what will D prime do? It will run D. If we run D, what will happen? D will ask queries. So D will, for example, ask, we don't know what exactly D does, but we know that probably D will ask queries. And D will ask queries expecting that they will be answered either with this function here, either this with f2, or with the properly random function. So how does D prime answer the query of D? If D asks for the function value of x, then what will D prime do? It will basically flip all of the bits in x, and then ask this as a query to its oracle. So the code of d prime at this point would be so whenever d prime will run d, and whenever d queries x, then d prime will query one XOR x. It will get some result y from its oracle, and then it will give this result back to d. So why does this make sense? Let's take a look at what happens if we run this d prime this way in the two different worlds. Okay, so let's do the case distinction essentially. So let's say d prime actually runs with the pseudonym function fk. Then it will query one XOR x as always, and then it will get as a result, it will get fk of 1 XOR x. Okay, and well, the nice thing is that this is exactly the definition of this fk2 that we have. So what the result here is actually fk2 of x. So if it then gives this value back to d, then if d prime is in the world where it talks to a pseudonym function, then for d, it will also look like it's in the world talking to the pseudonym function, to its pseudonym function, maybe to fk2. Now let's take a look at what happens if d prime talks to a properly random function. Well, the query is still the same because obviously that's what the code does. And the result that it will get is just f of 1 XOR x. And then you would give that value back to d. And now the hope is that if d prime is in the world where it talks to a properly random function, then also for d, for the inner d, it will look like it will also talk to a properly random function. Why is this? Well, we can do some formal analysis here, but the idea would be that there are basically two cases. So in the one case is if d has never queried for this x before, then also d prime will have never queried for this 1 XOR x before. And so the result of this function here will just be, from the view of d prime, it will be properly random. And so also for the view of d, it will also be properly random. Like d would also expect, if it queries a new x, it will get a properly random value back if it's in the world with the properly random function. If d queries an x that it has queried before, then d prime will also just query the same flipped x, will get the same answer as before, and so also this would be consistent to what d would expect querying the same thing again. So overall, if d prime is in the world with the pseudonym function, then for d it will also look like it's in the world with its pseudonym function, fk2. If d prime is in the world with the properly random function, then for d it will also look like it's in the world with the properly random function. So now we can finish this whole thing. So at some point d will stop asking queries, and it will output a bit b. And what will d prime do? It will also just output a bit b, the same bit b. Okay, so essentially in the code, it will just output the bit of b. And then we can analyze the actual success probabilities, which is just formalizing what we've seen before. So what we need to analyze is the probability that d prime, given oracle access to fk, will output 1. And well, from how we constructed this, we know that this is the exact same probability that d will output 1 if it interacts with the oracle for its pseudonym function f2k. And then the other thing is the probability that d prime that we constructed outputs 1 if it's given access to a properly random function. And well, the way that we constructed this, what we talked about here, we know that this is also just the probability that d, well, it outputs the bit of b. So the probability that D prime outputs 1 is basically the probability that D outputs 1. What we can then say is if we take the difference of these two, then this is equal to the difference of these two. And well, what do we know? We know that Fk, so not Fk2, but Fk, the original PRF, this is a secure PRF. So this here, for the distinguisher D prime that we did, this has negligible distance, meaning that also this here has the same negligible distance. And this concludes the proof, because we started with an arbitrary distinguisher D, and we ended up showing that the probability, also the distinguishing advantage of this arbitrary distinguisher D is negligible. So we know that Fk2 is a pseudo function. Yay. So let's take a look at the last one, which is F3. And F3 will take its input k and x, and then it will evaluate a pseudo function on k concatenated with x, and then just truncate this to the length that it wants to output. Okay, because pseudo functions are length preserving, so we would expect that if we take x with the length of n, then also fk3 of x should probably be of length n. Okay, so we just truncate this to n bits, which is also the length of k, which is what we're doing here. Yeah, so forget the truncation. This is just a technicality. But yeah, what we do is we apply a pseudo function to k and to x. And at first glance, this kind of looks okay, because at the very least, we are using the secret key k, and we are using the input x. So the standards are kind of covered. So this has a little bit of a chance to be a pseudo function. But, well, take a little bit of a think about it, whether it is. Okay, I guess I gave it away a little bit. This is not necessarily a pseudonym function. There are probably pseudonym generators for which this may be a pseudonym function, but in general it isn't. And this is because of a fundamental difference between pseudonym functions and pseudonym generators. And this difference boils down to the following. If I take a pseudonym generator G and I apply it to some random value R, then what I get is like a larger random value, capital R. Okay, so if this is random, then this also looks random. This is what pseudonym generators do very well. If they get random input, their output will also look random. What pseudonym generators don't do well is if I give it just the input 0, then this will not be random at all. Because it's a constant, right? It can't look random. There's no randomness involved at all. Essentially, you could also just evaluate G at 0 and you will get the exact same string, meaning that it won't look random to you. On the other side, if I take my pseudonym function and I apply it to 0, I will get something that looks random. If I take my pseudonym function and apply it to 1, I will get something that also looks random and looks independent of the first random value. Okay? So essentially, I can, with my pseudonym function, I don't need to change much in the input. I can change like a single bit, and I will get a completely different looking random string. If I do the same in the pseudonym generator, I get no guarantee, because the pseudonym generator guarantee only says that if I put something random in, I get something random looking out. But well, some of these are not random looking, especially if I just take 0, 1, and etc. And this generalizes to some other situations. So for example, if I take a pseudonym generator, and we had this in one of the exercises before, I think, and I give it some bit, then some other seed, a random seed, and so a random bit and a random seed, both of these are random. Then I will get a random looking image, right? So this works. But then if I do this a second time and I use the same bit, but a new random seed, then this will not look random. Again, this is because pseudonym generators only say something about if you take a new, fresh, completely independent random input, then you get something that looks random as output. But if you take like two related inputs like this, which have the same B, then, well, there's no guarantee that the two things that will come out of this will not look somewhat similar. So one particular example illustrating this is if I can construct a pseudonym generator that takes input like this, and it will output the bit B in plain, and then run the rest of the string through another pseudonym generator. And then this is actually a pretty good pseudonym generator, because with this bit B is not only pseudonym, it's actually random, because from the in the scenario where you want to use PRGs, this B is random, so this B is also perfectly random. And then this is a pseudonym value. So all of this works. You showed this before, I think. But if we apply it in this scenario, then obviously the first bit of R will be B, and the first bit of R prime will also be B. So these two won't look independent at all. They will definitely, with probability 1, have the same bit in the first position. And then we can apply all of this to this exercise here. For example, we want to show that this is not necessarily a pseudonym function, right? So we can come up with a counterexample for a secure pseudonym generator where this F3 is not a pseudonym function. And we basically already came up with it. It's this pseudonym generator. And if we do this here, then this will mean that all of the function values of F3, they will all start with the same first bit, which is the first bit of the key K. And then this won't look random, so it's easily distinguishable from a properly random function, because in a properly random function, the first bit will change with probability 1/2 each time. And here it's always the same. So we can easily come up with a distinguisher that asks several questions and then looks whether or not it's all of the first bit is always the same, which happens with probability 1 in F3, and it happens with probability 2 to the minus number of queries in the actual random function. Sorry, number of queries minus 1. And then we have this distinguisher, and then we can see that F3 is actually not a pseudonym function. That's actually it. Thanks for listening, and we will see each other in the next tutorial video.